With the all-important Euler's identity in our back pocket, we were finally able to define what the exponential function would be in the complex sense. So what would the function f of z equals e to the z mean for a complex input and a complex output? Euler's identity gives us all the tools that we need in order to start exploring the exponential function and what it can do for us. And from there, also figuring out what a logarithm, an inverse to the exponential function, might look like. So just to recap of our hard-won victories from the last couple of videos, by thinking carefully about the properties of the polar form of a complex number, we were able to make this key discovery that when I multiply complex numbers, the moduli of those complex numbers multiply, but the arguments add. And that led us to this hypothesis that the argument of a complex number is really somehow an exponent. And we just needed to figure out what the base of that exponent ought to be. And so then in our second video, we discovered what that base was by pulling out Maclaurin series. So these series expansions of the cosine and sine functions that we learn in second semester calculus. And by doing some nifty arithmetic tricks with the powers of I, we combined those series together and then discovered that really what we have is the exponential e to the power I theta is equal to, at least formally equal to, cosine of theta plus I times the sine of theta, which was what we called Euler's identity, or sometimes it's called Euler's formula. So why is this such an earth-shattering revelation for us when we're studying complex functions? That's because it allows us, at least formally, to define a complex exponential function. And so we're going to denote it by f of z equals e to the z. Sometimes if we have a bunch of stuff in that exponent and it's going to get hard to read, we'll write it using exp of z. That might also be how you see it on a calculator, if your calculator knows how to take the exponentials of complex numbers, which I believe the TI graphing calculators do not. But you can correct me in the comments if I am unaware of the recent advances in graphing calculator technology, which move at about the speed of a receding glacier. Anyway, so how might we define the complex exponential function, knowing what we know about Euler's identity? Well, let's just use what we hope are properties of exponents to say if I have a complex number in its rectangular format, x plus I times y, then e to the x plus iy should be the same thing. Again, adding exponents should be the same thing as multiplying powers. And so I can take that x plus iy from the exponent and make it multiplication of the powers, so rewrite it as e to the x times e to the iy. Now, x is a real number, and y is a real number. So e to the x is the familiar e to the x that we know from high school. E to the iy, because y is real, we can stick that through Euler's identity and figure out that e to the iy is just cosine of y plus I times the sine of y. And so when I multiply these out, I get e to the x cosine y plus I times e to the x sine y. In other words, the complex exponential function has real part, e to the x cosine y, and imaginary part, e to the x times sine of y. So definitionally, that's our complex exponential function. We're going to study some of the transformational, the mapping properties of this function in our next video. But for now, suffice to say that it's most helpful for us in understanding the complex exponential function when the inputs to that function are in their rectangular form. Notice that the formulas here, the real and imaginary parts, are expressed in terms of x and y, the real and imaginary parts of the input. So having our inputs in rectangular form is really the best way to help us understand the complex exponential. So let's apply this idea to do some computations. I mean, if we know what the complex exponential function is, it tells us how to take the exponential of any complex number that we might stick into it. Let's do some examples. Like, what might e to the power I be? Well, we can just run this through Euler's identity. I is just 0 plus 1i, so the role of x here is being played by 0, and the role of y is being played by 1. So e to the I is cosine of 1 plus I times the sine of 1. And if you like approximations, which I usually don't, it's approximately equal to this. So we know how to compute e to the I. What about other exponentials? What if the base is not e? Could we do 2 to the I instead? Well, here again, we pull out our high school properties of exponents training, and we remember how it is that we can change base in an exponential expression. And we can get away with this right now because both e and 2 are real numbers. And so I know for sure that I can rewrite 2 as e to the power natural log of 2. So 2 to the I is e to the natural log of 2 raised to the ith power. And since taking a power to a power leads to multiplication in the exponents, we can rewrite that as e to the I log 2, right, where that log is just the ordinary natural log from high school. Now we can run that through Euler's formula with the role of x being played by 0 again, and the role of y being played by the number natural log 2, to find out that 2 to the I is actually cosine of the natural log of 2 plus I times the sine of the natural log of 2. And again, there's an approximation for those of you who like that kind of thing. All right, let's take it a little further, if we can. What about I to the power I? Well, we can't take for granted that we can use the subterfuge that we used in the 2 to the I case in this example. And that's because our original base here that we're trying to compute with is not real, but the new base that we would try to compute with to use Euler's formula, e, is real. So we haven't made sense of complex logarithms just yet. That's going to happen in our next video. If we could somehow do that, right, then I to the power I could be rewritten as e to the I log I. And we could rewrite that then as cosine of the log of I plus I times the sine of the log of I. But we have to put giant scare quotes there around ln of I, because that is a meaningless expression. Throughout these videos, I'm going to use ln to denote the high school real function of a real input and a real output, which we know as the natural log, which is the inverse of the real exponential function. So ln of I is not something that I'm ever going to write as though it makes sense. So do not take this formula over here as literal. You can take it seriously, but don't take it literally, not just yet. We haven't made sense of the logarithms of complex numbers. So that's going to be our next task. How can we understand the mapping properties of the exponential function in such a way that allows us to invert the complex exponential function to discover a complex logarithm? Stay tuned.